Threat actor TeamPCP is back, and their deployment strategy is designed specifically to bypass standard static analysis. Instead of embedding large, easily detectable malicious scripts directly into open-source packages, they have pivoted to using thin droppers. The actual credential harvesting code is now smuggled inside the frame data of structurally valid .wav audio files. Because the file passes MIME type checks and looks identical to a harmless ringtone, network content filters and automated package scanners let it enter the environment. By decoupling the package from the malware, TeamPCP ensures that the code sitting on the registry reveals nothing about the actual attack logic. The target for this specific attack wave is the official Python SDK for Telnyx, a package downloaded nearly 800,000 times a month. Telnyx handles telecommunications routing, meaning its SDK is deeply embedded in backend services and continuous integration pipelines. By design, this SDK operates in environments saturated with telephony API keys, session secrets, and webhook credentials. Capturing these specific telecommunications credentials grants an attacker authenticated access to route voice services and intercept downstream infrastructure communications. Threat actors select targets where the natural operational environment guarantees the highest possible density of secrets per infected host. If you check the Telnyx GitHub repository, you won't find a single malicious commit or suspicion they gained 3 days earlier during their compromise of the LiteLLM Python package. This diagram shows the credential cascade. When the LiteLLM harvester infected developer workstations, it swept them for exposed PyPI publishing tokens, PyPI being the official software repository for Python. One of those tokens belonged to a maintainer with publish rights to the Telnyx SDK. Using that stolen credential, TeamPCP published malicious versions 4.87.1 and 4.87.2 directly to the registry. This direct publish method circumvented branch protections, code review, and automated security pipelines. Securing a source code repository offers little protection if long-lived registry publishing tokens are left exposed on downstream developer machines. TeamPCP deployed their first malicious package, version 4.87.1, at 0351 UTC on March 27th. However, the code contained a syntax error. A capital S in the setup function call caused a Python name error, which stopped the payload from executing. Looking at the central payload timeline in this intelligence report, the attackers noticed the failure immediately. Exactly 16 minutes later, version 4.87.2 went live on PyPI, correcting the typo and enabling the full attack chain. This 16-minute turnaround highlights a highly agile deployment style, a pattern researchers refer to as vibe-coded malware. Threat groups are now actively identifying syntax errors in the wild and iterating on production package registries in near real time. The execution begins the moment a user imports the Telnyx module, triggering modified code injected into the _client.py file. The file does not contain the group's full credential harvester. It only holds a lightweight 4,428-character dropper script. This dropper executes an HTTP GET request to a bare IP address to download what appear to be standard .wav audio files. The file arrives with standard headers, looking like a harmless audio file, but the frame data isn't sound. The script extracts the frames, decodes the base 64, and isolates the first 8 bytes as an XOR key to decrypt the true Python payload. Because the payload is assembled purely in memory from a valid audio file, the actual malware code is not visible to static analysis. Once the core payload is decrypted in memory, it queries the host operating system to decide how it will establish persistence. This intelligence diagram illustrates how the malware splits its execution strategy between operating systems. On Linux and Mac OS, Fetch Audio installs a persistence layer named audiomon.service using systemd. The Windows path, new to this campaign, extracts a native executable from a different audio file named hangup.wav. This executable drops itself into the Windows startup folder disguised as msbuild.exe, utilizing a hidden lock file to enforce a 12-hour cooldown period between executions. TeamPCP's framework uses this initial access to deploy platform-specific persistence, whether that's a Linux systemd service or a Windows startup binary. The decrypted payload immediately begins sweeping the local file system for SSH keys, database configurations, and active cloud metadata tokens for AWS, Google Cloud, and Azure. But the most severe threat materializes if the payload detects it is running inside a Kubernetes environment. The malware uses the pod's stolen service account tokens to target the kube's system namespace, the core control plane of the cluster. From a single compromised worker node, the attacker deploys highly privileged pods outward to every other node in the cluster. These pods mount the host root file system, allowing them to install the audio mondad service implant directly onto the underlying host operating system. The ability to mount the host file system and install a node-level service converts this from a transient script into a permanent infrastructure foothold. If you use this SDK, the immediate required action is to verify your installed version and downgrade to version 4.87.0. Because the malware runs outside the Python environment, you must manually delete the AudioMon service on Linux, remove the fake msbuild.exe from Windows Startup, and terminate any node setup pods in Kubernetes. Most importantly, you must execute an atomic rotation for every single credential that was reachable from the infected host, including cloud access tokens, database passwords, and SSH certificates. In modern supply chain attacks, the installed code is often just the trigger. If you don't hunt down the persistent artifacts, the malware remains active long after the package is gone.